Welcome to Lecture 2B. Title is Limits and Existence of a Limit. And so this is the second lecture in a series of 3 for Lecture 2. Material for this particular lecture can be found in Chapter 15.2 of the textbook. Objectives are determining the existence or non-existence of a limit for a multivariable function and illustrate methods used to determine if the limit exists for two variable problems. So the focus on there is on using tools to determine if the limit exists in this particular lecture. Concepts and definitions. Methods for converting a problematic function into rational functions for which the existence or non-existence of a limit is easier to prove. And there are 3 approaches that we can typically take. One is to factor the numerator, second is algebraic conjugate method, and the third is change of variables. We'll discuss examples of each one of these 3 cases. Okay, so as usual, this is just a summary of the slides that will be covered. I'll just move on since these are just the details. All right, so first of all, we're going to start with some basic limit laws. And there are 2 theorems here that we consider. One is the limits of constant and linear functions. And the second theorem is limits of 2 variables. Okay, so these can be proven using the delta epsilon method. We're just going to state them as they are. So there is one for constant function, determining the limit for a linear function in x and a linear function in y. And then there are various operations that you can perform on functions. So for instance, sum, difference, constant, multiple, product, quotient, power, and root. And basically it's saying that if you can show that the limit of one function exists and a limit of a second function exists, then the operation on those 2 functions will provide a new function whose limit also exists. So these basically again can be proven using delta epsilon method. And typically, we will not basically go into the details of proving these things. It'll just be understood that for polynomials, rationals, and algebraic functions in 2 variables, right, we know that the limits exist so long as you're within the domain of the function. So again, these are basically just the particular laws that we'll be making use of. Okay, so let's take the basic limit laws. Which is a direct proof example. So basically it's saying if this and that exists, then the outcome exists. So we're going to take the function here, z is equal to 3x squared y plus square root of xy, and we're interested in knowing whether or not the limit exists as x and y approaches 2,8. Now for this particular function, we need to know the domain and the range. The domain is limited because of the square root. So as long as the product of xy is greater than or equal to 0, then essentially all other values of x and y are admissible. The range in this case you can show can be any element of the real number set. Now if we were to plot this domain that is on the xy plane, you'll notice that the domain will include all possible combinations of x and y in the first and third quadrant, including the x-axis and the y-axis. That's why I've shown it as a solid blue line, because it's basically a closed set. All right, so how would we go about proving this particular function's limit existence? We basically start by making use of all the specific limit laws that we discussed in the previous page. And so let's start with x squared. Well, we know that basically by law 6, the limit of this exists. Then we look at x squared y. Well, the limit of this exists by the product law. Then we multiply by 3, and we find that the limit exists because of the constant multiple law. Then we move to the second term. xy, the limit exists because of the product law. The square root of xy exists because of the 1 over n root law. And finally, we add the 2 functions together, and basically the limit exists because of the sum law. So effectively, this is the sort of procedure used to prove the limit exists. You could have done it in a different sequence of steps, which is fine. We're not going to ask you to go through this procedure every single time when you see rational functions. This just shows you how it would have been done on a relatively simple problem. All right, so let's look at then the second case, which is a factoring of the numerator. And again, it's a direct proof example. There is an interactive diagram on the next slide, just so that you know that you've got something you can actually play with and try to understand graphically what it looks like. You're given that the function z is x squared minus y squared over x minus y, and you're interested in determining what the limit is as xy approaches 4, 4. Now, always look at the denominator because that's already a telltale sign that we might be in trouble. And sure enough, the xy 4, 4 would give you a denominator of 0, which means we have a problem. And so we call 4, 4 as a boundary point. In other words, we can't really get onto this point or series of points since x and y can take on combinations of values. So in this case, the domain would be all x and y except x equals y. And the range in this case would be all values of z. You can show that to be the case because the numerator can be positive or negative depending on the value of x with respect to value of y. Okay, so in using the factoring numerator approach, we need to take the numerator and just factor. It's a quadratic equation. And so x squared minus y squared is similar to x plus y times x minus y, divided by x minus y. Well, the x minus y on the numerator and denominator factor out, and you end up with final solution of x plus y. Now, the limit of that function exists, again, according to the sum law, because if the limit x exists, it does, and the limit y exists, it does, then the limit of the sums also exists. So you can just more or less substitute the value for x in and the value of y, and you'll end up with a value of 8. All right, so this is the interactive diagram I mentioned you can play with. Notice again that y equals x is excluded from the graph because x equals y is not part of the domain of the function. Anyways, look at this particular interactive diagram to help you visualize the problem. All right, let's look at this function again in a little bit more detail. We want to basically determine what that line is and also graph what the domain looks like. So if we take the final result that we obtained, that z was equal to x and y, x plus y, then if we want a line, then we need to basically parameterize. So for instance, we could choose x to be t, and that y would therefore be dt because it's and then the sum of the two would just be 2t. And t is an element of R, right? So that basically would be the equation of line. You could also write it in position vector form, in which case we would just angle bracket x component t, y component t, z component 2t. So this is basically the position vector that you would see. In the xy domain, you can see the domain. The line y of x, which is a dotted blue line, is not part of the domain. So it's everything else basically is part of the domain. So this is just an illustration for this particular problem, and just trying to graph as much as possible. All right, let's look at another option, which is the algebraic conjugate direct example approach. So let's say you are given a function xy minus 4y squared divided by square root of x minus 2 square root y, and you're interested in looking at the limit as xy approaches 4, 1. Well, clearly, if you plug in the values of 4 and 1 in the denominator, you'll end up with a value of 0, which means 4, 1 is a boundary point. So we'll have to exclude it from the domain. And so the domain in this case would be, because square root can only be square roots would have arguments that must be greater than 0, means that x is greater than or equals to 0 and y is greater than or equals 0. Also, we have to make sure that the root of x minus 2 root y is not equal to 0. So there are 3 conditions that have to be satisfied. Right? It turns out also that, as we'll show later, that z must be greater than or equal to 0 as well. At this point, it would be difficult to determine, but at the very end, it'll be obvious that it must be greater than or equal to 0. All right, so what is the solution going to be? Well, the solution in this case, you look at the denominator and you realize it's square root of something minus something square root. So if we were to multiply top and bottom by the conjugate, which is basically just to flip the sign, so that becomes square root of x plus 2 square root of y, top and bottom. That ratio is 1, which means we haven't changed the nature of the expression. However, what it does allow us to do is to simplify the denominator term, and so the denominator term becomes x minus 4y. On the numerator, you'll have the root x plus 2 square root of y, and also you'll have xy minus 4y squared. So that can be further simplified because in the numerator, y is a common multiplier, and so you'll end up with x minus 4y on the numerator times y divided by x minus 4y, which means you end up with a y. So the final result is y times square root of x plus 2 square root of y. And again, by the theorems that we talked about before, you can show that the limit for this expression exists, and it turns out to be 4. Now we're talking about what the range is. Well, if you look at the values here, you'll realize x must be greater than or equal to 0, and y must be greater than or equal to 0. Okay, and so that basically means that also y has to be greater than or equal to 0, which means the values can only, z values can only be greater than or equal to 0. And so that's how we get the range that was shown earlier. If you look at a sketch, then basically the expression root x minus 2 root y not equal to 0 is equivalent to saying it is a line that is x equals 4y, and it's not part of the domain. All right, and the boundary point is on that line, and that's designated in the diagram as position 4,1, which is right there. All right, we can also graph this function. So let's do that. And so I've made use of the 3D math program. You can click on it and play around with it if you want. Anyways, the blue line is basically the line in the XY plane. And then you can compute what the Z value is as you move along the XY plane. And that's the red line that you see, which lies on the surface. Now, in this case, the surface is curved because the function was nonlinear. Right, so that's why you have this sort of funny looking shape. And so if we graph this out, we basically would have, you have to parameterize a line, so you would have x is some function of t. The simplest thing is just to call it t, right? You have y equals 1/4 x, so if x is t, then y becomes 1/4 t. And then substituting for x and y into the original function, you can get z as a function of t. And that's precisely what we do in the next step here. So there's x of t equals to t. Y of t is equal to 1/4 t, because it's the line we're interested in. And then substituting x and y in for the equation for z, you end up with the expression shown there. And then after some simplification, we end up with 1/2 t to the power 3/2. And t has to be greater than 0, again, because of constraints on x and y. If you want to put this in a position vector form, Matt, then basically you take the x, y, and z components in parameterized form and put them in an angular bracket. So the position vector basically is a vector that points from the origin to every point along the line on the surface. All right, and the last technique is called change of variables. We want to determine if the limit of z equals limit of xy going to 0, 0, x squared y divided by x squared plus y exists, and if it does, compute its value. So the solution basically is to first identify that 0, 0 is a boundary point for the function x squared y divided by x squared plus y squared. And so the technique we use in this example is to let z be some function of u and v. That is, x is a function of g of u of v, y is a function h u and v. And there are many types of transformations you can use, but the simplest ones, the ones we're going to be used most frequently, are basically polar coordinate transformations. And how do we know that? If you look at the denominator, it's x squared plus y squared. That begs polar coordinates. And so that means, for instance, x will be replaced by v cos u, y will be replaced by v sine u. The limits on v are v greater than or equal to 0, and u is between 0 and 2 pi, right? This is typically used if you know that the boundary point is at 0, 0. Otherwise, you would have to make some modifications to the function that you substitute. Note, the mapping that for u and v to x and y should be 1-to-1 and onto. So you don't want mapping to essentially count a particular point 2 times or more. So it's literally going to be essentially 1-to-1. You would take a point xy and there's a unique position uv in the uv plane. Okay, so now that we basically know what the transformation is, we substitute x equals v cos u and y equals v sine u into the function x squared y divided by x squared plus y squared. Now we have to note that the transformation of xy at 0, 0 is going to be a transformation in vu, which will have the form 0 and u. The only way basically that you're going to get 0, 0 is by setting v equal to 0. All right, but u can be anything. All right, so you make the substitution. In this case, v is going to 0. And after substituting for x equals v cos u, y v sine u, the function simplifies to v cubed cos squared u sine u divided by v squared, which just becomes v cos squared u sine u. Again, because these are rational functions, you know the limit will exist. And since v goes to 0, it doesn't matter what u is, because cos squared u is bounded, sine u is bounded, the result is 0 for all possible u, and those represent paths. So if you look at the picture on your right here, okay, this direction is u, which is in a radial direction. Oh, sorry, this direction here basically is v, which is in a radial direction, and u is a circumferential direction, that is in a counterclockwise direction. So by fixing a particular value of u, we're sweeping out the value of v from 0 to infinity. So that's a path. If you now change a different value of u, then you'll have a different radial line. But in all cases, we're coming back to the center. So the limit in all cases, no matter how we choose u, is always going to be equal to 0. All right, therefore, the limit exists in this case. All right, so we made use of the product law, basically to prove that the limit exists. And a was greater than or equal to 0. So this a just refers back to the fact that v must be greater than or equal to 0. And also just to sort of, if you have a more complex function where you can use this substitution, and it turns out that the argument of the limit contains a multiplicative term of the form v to the power n, where n is greater than 0, then again the limit will exist, because as v goes to 0, v to the power n will go to 0. So that concludes lecture 2b. Thank you for listening.